Before anything existed, the universe faced its first and most important decision. This was the moment of the very first quantum superposition, a state where all of reality was pure potential, an undecided blueprint for everything to come. We are going to explore 30 incredible theories that attempt to explain this primordial event. You will gain a complete picture of how our cosmos might have chosen its fundamental laws from a sea of infinite possibilities. We will see how cosmic inflation could have been a quantum roll of the dice, and whether our entire reality is just a holographic projection. The answers to these questions define the very fabric of our existence. What does it mean for our reality to have started as a question mark? The first theory takes us to the very edge of existence, to a moment before time had a clear meaning. Before there were stars, planets, or even atoms, the cosmos was dominated by a single, all-powerful force known as the inflaton field. This was not a field you could walk across, but a fundamental energy saturating the newborn void, a pressure cooker of pure potential. Within this field, the first quantum superposition occurred. It was a state of profound indecision, where the rate of the universe's explosive expansion and its energy density were not yet fixed. The entire cosmos existed in a shimmering haze of what-if, a superposition of countless different possible futures. In one potential reality, the expansion might have been slightly faster. In another, the energy density could have been a fraction higher. For a fleeting quantum moment, all these realities were equally true. Then, this vast, undecided state collapsed. The superposition resolved, choosing one specific path from the infinite menu of possibilities. This single, definitive outcome is what we see imprinted across the sky today. The subtle variations in the cosmic microwave background, the vast cosmic web of galaxies, all of it can be traced back to that first monumental decision. Our entire observable universe, in all its splendor, is the echo of a single fluctuation in a field that no longer exists. This leads us to a theory so profound it redefines the meaning of beginning. The second theory posits that the entire cosmos was born from a single, all-encompassing wave function. Stemming from the Wheeler-DeWitt equation, a cornerstone of quantum cosmology, this idea states our universe did not merely contain a superposition. It was a superposition. Before any classical reality emerged, the universe existed as a blend of every conceivable starting point. It was a shimmering potential of all possible geometries, from perfectly flat to wildly curved. It held every potential topology, from a simple sphere to a complex, multi-connected shape, and it contained every possible arrangement of matter and energy, all existing at once. Think of it not as a single seed, but as a quantum forest containing the blueprint for every type of tree that could ever grow. In one branch of this universal wave function, the fundamental constants might have been slightly different, making gravity weaker. In another, space itself could have had more dimensions. For a timeless moment, all of these complete, self-consistent universes were equally real, layered on top of one another in a state of pure potential. Then something happened. A process which we might call a measurement or decoherence caused this vast superposition to collapse. Out of the infinite choir of possible realities, one single universe was selected, its specific geometry, topology, and physical laws frozen into place. The cosmic roll of the dice was not for a single property, but for the entire character of existence. We are not just living in the outcome of that first quantum decision. We are living as that outcome. This is a universe without a true beginning, a cosmos that never experienced a definitive starting gun. The third theory, the no-boundary proposal by Stephen Hawking and James Hartle, reimagines the origin of everything by erasing the very concept of a first moment. They proposed that the universe has no initial boundary in time, no sharp edge where physics breaks down. To understand this, picture our planet. The the North Pole is a real place, but if you stand directly on it, the very idea of north loses all meaning. Every direction you face is south. The North Pole is not a boundary to the Earth. It is simply a point where our conventional coordinates become inadequate. Hawking and Hartle suggested the birth of our cosmos was similar. There was no singular point of creation, no t=0 where the laws of physics surrender. Instead, the universe emerged from a fuzzy, superposed state of all possible finite, four-dimensional geometries that smoothly closed off the beginning. In this primordial state, the distinction between time and space becomes blurred, replaced by what is called imaginary time. This is not time as we experience it, but a mathematical dimension that allows for a seamless, rounded-off origin. The first great superposition was not a fluctuation within a field, but a simultaneous existence of every single possible history of this imaginary time. One potential geometry might have been a perfect sphere, another a slightly squashed oval, and another a more complex, wrinkled shape. All of these self-contained, finite universes without a singular start point were equally real, layered atop one another in a state of profound quantum potential. Our classical universe, with its clear arrow of time, then crystallized out of this superposition, selecting one specific geometry from the infinite menu of smooth, boundary-free options. We are not the aftermath of an explosion from a point, but the unique classical reality that precipitated from a timeless, boundless quantum fog. The very fabric of reality was once a seething ocean of pure uncertainty. This fourth theory plunges us into the Planck epoch, the first fleeting moment of the universe's existence, a duration so short it defies human comprehension. During this era, gravity was not the steady, predictable force we know today. It was a quantum actor, and its quantum nature meant that spacetime itself was not yet a stable stage. It was the stage, the actors, and the script all in a state of turbulent indecision. This was the realm of quantum foam. Picture the surface of a boiling pot, but instead of water bubbles, these were bubbles of spacetime, constantly flickering in and out of existence. In this foam, the concepts of cause and effect broke down. Two events could be causally connected in one potential reality and completely disconnected in another. Distance and duration lost their fixed meaning, with the very geometry of the cosmos existing in a profound superposition. One moment, spacetime might have been tightly curled into 11 dimensions. The next instant, it could have been a vast, flat, four-dimensional expanse. It was a churning sea of all possible spacetime configurations, each one a complete and self-consistent geometry for a potential universe. This was the first and most fundamental superposition, a fluctuation in the bedrock of existence itself. Then, as the universe expanded and cooled in those first unimaginable fractions of a second, gravity underwent a profound transformation. It decode. It lost its quantum fuzziness and crystallized into the classical force that governs the fall of an apple and the orbit of a planet. In doing so, it forced a single, stable geometry of spacetime to emerge from the quantum foam. Our familiar reality, with its clear forward flow of time and three dimensions of space, is the one configuration that was selected from that infinite, frothing sea of possibilities. The universe did not simply form within spacetime. Spacetime itself was the first and greatest quantum decision. Our universe could be just one page in an infinite cosmic library. The fifth theory, the multiverse genesis, proposes that the very first quantum superposition never truly ended. There was no single, definitive collapse into one reality. Instead, that primordial state of indecision, that shimmering haze of what if, simply branched out. Every single possible outcome of that initial fluctuation was realized, each one birthing its own separate, self-contained universe. Our cosmos, with its specific laws and constants, is merely one branch of that initial, all-encompassing cosmic wave function. In one branch, the inflattened field decayed slightly faster, creating a universe that expanded more rapidly and grew far more diffuse. In another, the fundamental strength of gravity was a fraction stronger, leading to a cosmos where stars burned out in a cosmic blink. The first superposition did not choose one path. It created every path. This means the very concept of a single beginning is an illusion. That first quantum decision was not a roll of the dice with one winner. It was the dice shattering, with every single face landing upright in its own pocket of reality. The multiverse genesis tells us that our existence is not the result of a lucky break, but a statistical certainty. Somewhere in the vast expanse of all that is possible, a universe with life was bound to emerge. We are not special, we are simply one expression of an infinite cosmic potential, a single note in a symphony of realities that has been playing since before time had a single, unified meaning. But death for a universe is not an ending, only a transformation. The sixth theory, Roger Penrose's conformal cyclic cosmology, presents a breathtaking vision of cosmic rebirth. It proposes that our Big Bang was not a singular beginning from nothing, but a quantum bridge from a previous cosmic era, which Penrose calls an eon. In the far, far future of that previous eon, all matter would have eventually decayed into massless particles, and the universe would have expanded into a state of featureless maximum entropy, a cold and silent void. In this final state, where there are no rulers or clocks to measure distance or time, the universe becomes smooth and simple once more. It is at this point of ultimate dissolution that a profound quantum superposition occurs. The entire quantum state of that dead universe, in its final moments, enters a superposition. It exists in a state of being both the final end of one cycle and the potential beginning of another. This superposition is the bridge. It is the moment when the fading echo of one cosmos undergoes a quantum reset, its infinite scale conformally transformed into the unimaginably hot, dense seed of the next. The first superposition of our universe was not an event within time, but a transition between times. It was the quantum decision that allowed all the information of a dead reality to be lost, while its fundamental geometry was recycled, giving rise to our own vibrant Big Bang. We may be living in the aftermath of a cosmic phoenix, born from the quantum ashes of a world that came before. Reality itself may be the ultimate illusion, a cosmic mirage projected from the edge of space and time. The seventh theory, the holographic principle, proposes that our universe is not fundamentally three-dimensional at all. Everything we see and feel, every galaxy, every planet, and every one of us, could be a holographic projection of information encoded on a distant, two-dimensional surface. This leads to a stunning reimagining of that first quantum superposition. The very first moment of indecision did not happen within the volume of the universe. It happened on its boundary, on a cosmic horizon that surrounded the nascent cosmos. On this fundamental surface, the basic building blocks of reality were not particles or forces, but bits of quantum information. And in the beginning, these bits existed in a state of pure potential. Every single possible configuration of this holographic data was real at once, a shimmering superposition of every possible spacetime geometry and every possible arrangement of matter. One potential configuration might have described a universe with 7 spatial dimensions. Another might have encoded a cosmos where stars could never form. This was not a superposition of things within the universe, but a superposition of the universe itself, written in a quantum code on its outer shell. Then a process akin to decoherence occurred. This vast, undecided sea of information on the boundary collapsed, selecting one specific configuration from the infinite menu. It was this collapse that projected our specific, classical, three-dimensional reality into being, freezing the laws of physics and the structure of spacetime into the definite forms we observe today. Our tangible world of height, width, and depth is a grand translation, a cosmic readout from a flat, quantum hard drive that made its first and most important decision at the dawn of everything. The eighth theory shatters the idea of a singular beginning entirely, proposing instead a cosmic heartbeat. Loop quantum cosmology rewrites the story by suggesting our universe was born not from a void but from a collapse. In this view, a previous cosmic era reached the end of its life and began to contract, squeezing all matter and energy into an increasingly dense state. But instead of crushing down into an infinitely dense point of nothingness, a singularity, the quantum nature of spacetime itself created a repulsive force. This force turned the final crunch into the first bang of our own era, an event known as the Big Bounce. The true first superposition of our cycle was the quantum state of this very bounce. At that critical moment of transition, the universe did not have a single, defined fate. It existed in a profound state of indecision, a superposition of countless different possible densities and geometries. One potential reality at the bounce might have been slightly more dense, leading to a more rapid initial expansion for our universe. Another might have possessed a subtly different geometry, altering the fundamental forces from their very first moment. This was not a clear transition from one classical state to another. It was a fuzzy, quantum bridge where the dying breath of one cosmos and the first cry of another were inextricably linked. The universe was, for a timeless instant, both contracting and expanding, both infinitely old and brand new. From this shimmering haze of possibilities, a single, stable configuration for our expanding universe finally emerged. The Big Bounce was not a single event, but a quantum selection process, choosing the specific conditions that would define everything to come. Our reality is the echo of a decision made in the blurred space between one cosmic death and the next great birth. The value of nothing might be the most important number in the universe. This ninth theory confronts a mystery that has baffled physicists for generations, the cosmological constant problem. The vacuum of space is not truly empty. According to quantum mechanics, it is a seething sea of virtual particles flickering in and out of existence, and this activity imbues the void with a background energy. This energy, the cosmological constant, acts as a kind of anti-gravity, pushing the fabric of the cosmos apart. The puzzle is not that this energy exists, but that its value is so absurdly, inexplicably small. The math suggests it should be a number so vast it would have ripped the universe apart before the first stars could ever form. Yet we observe a value that is just enough to accelerate cosmic expansion without tearing everything to pieces. How did our universe get so lucky? The answer may lie in that first great superposition. In the beginning, the cosmological constant was not a fixed number. It existed in a state of profound quantum indecision, a superposition of every single possible value it could have taken. One potential reality possessed a constant with immense destructive energy. Another had a constant with negative energy, causing the cosmos to collapse back on itself almost immediately. Countless other universes with countless other values all existed at once in a shimmering haze of pure potential. Then a subtle process of decoherence began. As the first particles began to condense out of the energy fields, their interactions with the fabric of spacetime may have acted as a kind of measurement. This process collapsed the vast superposition, selecting one specific, incredibly tiny value for the cosmological constant from the infinite menu of possibilities. It was not a lucky break, but a quantum selection. The universe did not find its fine-tuning. It chose it, resolving a fundamental ambiguity in a way that accidentally made the cosmos stable enough for galaxies, stars, and ultimately for us to emerge. The emptiness of space holds an echo of that first and most critical decision. The steady tick of a clock feels inevitable, a fundamental rhythm of our reality. But this 10th theory questions that very assumption, proposing that time itself is not a primitive stage on which the universe plays out, but a property that emerged from a state of timelessness. Before the first great superposition, there may have been no before or after. The quantum state of the cosmos was static and unchanging, a frozen potential where every possible configuration of reality existed at once with no sequence to order them. This was a profound and alien state of being, a block of undecided reality without past, present, or future. The first moment was not a point in time, but the moment time began. It was the instant this timeless superposition collapsed, as the universe selected one specific configuration from the infinite menu of possibilities. It broke a fundamental symmetry. This act of decoherence created the first irreversible event, establishing a before and an after. The arrow of time, the reason we remember the past but not the future, is a direct relic of this initial decoherence event. It is the cosmic scar left by that first and most fundamental choice, a direction etched into the fabric of reality when the universe transitioned from being everything at once to becoming something specific, forever moving forward from that point of selection. Our relentless march into the future is not just a feature of the universe, it is the echo of its very first decision. The number 10 to the power of 500 is a figure so vast it defies any human scale. This is the staggering number of possible realities suggested by the 11th theory, the string theory landscape. In this view, the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating strings. The way these strings vibrate dictates everything from the types of particles that exist to the very strength of the forces that bind them. But for these strings to vibrate, they require a stable background, a specific configuration of the extra dimensions string theory proposes. Each of these stable configurations is called a vacuum state, and each one is a complete and self-consistent set of physical laws. One vacuum might produce a universe with 4 fundamental forces and the exact electron mass we observe. Another might yield a cosmos with only 2 forces and stars that could never ignite. The landscape of possibilities is not just large, it is effectively infinite. This theory proposes that the universe's first superposition was not of a single field or a geometry, but of this entire landscape. At the beginning, the cosmos existed in a state where every single one of these 10 to the 500 possible vacua was real at once. It was a symphony of every conceivable physics, all playing in a quantum chorus. There was no single law of gravity, but a superposition of all possible laws. There was no fixed set of particles, but a haze of every possible particle content, all coexisting in a state of profound potential. The first quantum event was the collapse of this ultimate superposition. A specific vacuum was selected from the near infinity of options. This single, random choice froze the vibrations of the strings into a specific pattern, locking in the number of dimensions we experience, the strength of gravity, the mass of the quark, and every other fundamental rule of our existence. Our reality is not just one possibility. It is one selection from a cosmic catalogue of universes so vast we can only write its size as a 1 followed by 500 zeros. A quantum handshake echoes across all of time. The 12th theory, the transactional interpretation, reimagines the very first event not as a solitary fluctuation, but as a conversation between the beginning and the end of everything. In this radical view, the newborn universe did not simply exist in a static superposition. It was actively reaching out, sending a call into the void. This was the offer wave, a quantum proposal radiating from the Big Bang into every possible future. It was a question mark made of pure potential, asking what kind of universe it should become. This wave traveled forward through the branching paths of time, encountering every possible outcome, every potential galaxy, every potential form of life. And from each of those possible futures, a confirmation wave traveled backward, answering the call. These were not physical particles moving in reverse, but quantum responses, echoes from destinies that had not yet happened. The first great superposition was this entire, timeless network of calls and responses. It was a shimmering web connecting the initial moment to every conceivable conclusion. One confirmation wave might have come from a future where the universe collapsed in a fiery big crunch. Another echoed from a future of endless, cold expansion into nothingness. For a quantum moment that transcended time, all of these transactions were equally real, a chaotic negotiation between birth and death. Then the handshake was completed. One specific set of confirmation waves from one specific future timeline resonated perfectly with the initial offer wave. This resonance collapsed the vast superposition, finalizing the transaction. It selected the single, consistent history we now inhabit, locking in the chain of cause and effect from the first instant to the final fate. Our reality is not a solitary path through time, but a closed loop, a deal struck between the universe's first question and its ultimate answer. The idea that reality requires an observer is a haunting one, but what if the universe needed no one to watch? Theories like the Garadi-Rimini-Weber or GRW model propose that wave functions possess a fundamental instability. They collapse on their own, spontaneously and randomly, as an objective feature of the world. This suggests the first and greatest superposition of the cosmos did not end because it was measured. It ended because its time was up, triggered by a built-in ticking clock within the fabric of quantum reality itself. In the ultra-dense furnace of the primordial universe, this process would have been incredibly rapid. A state of pure potential holding every possible configuration of matter and geometry could only exist for a fleeting instant before an intrinsic random fluctuation forced a choice. One moment, everything was possible. The next, a single, definite reality crystallized from the quantum haze, not because a conscious mind willed it, but because the mathematics of existence demanded it. This was not an observation but a cosmic inception, the first click of a quantum metronome that set the stage for everything to come. The profound implication is that this initial, objective collapse event might have left a permanent scar on the sky. The sudden transition from a blurry quantum state to a sharp classical one would have released a burst of energy, creating subtle, specific patterns in the very first light of the cosmos. Scientists are now searching the cosmic microwave background, that ancient afterglow of the Big Bang, for the faint statistical signature of this first great collapse. Finding it would be like discovering the fossil of creation itself, proof that our reality was born not from a watchful eye, but from a random, fundamental pulse in the heart of the quantum world. The acceleration of our universe is driven by a force we cannot see, dark energy. Theory 14 proposes that this mysterious presence is not a new actor on the cosmic stage, but a frozen relic of the very first quantum decision. In the beginning, the field responsible for dark energy was not a fixed entity. It existed in a state of profound superposition, its potential energy fluctuating between every conceivable value. One moment it could have held immense energy poised to rip spacetime apart. The next, it might have possessed almost none, leaving the universe to collapse under its own weight. This field was a sleeping giant of pure potential, its fate undecided. Then, as the cosmos expanded and cooled, it crossed a critical threshold. This triggered a cosmic phase transition, much like steam condensing into liquid water. This process forced the field's wave function to collapse, locking it into one specific, stable configuration from the infinite menu of possibilities. The energy inherent in that chosen state did not disappear. Instead, it was frozen into the fabric of the vacuum itself, becoming a permanent feature of empty space. This is the dark energy we observe today. Its strangely small but persistent value, which now gently pushes galaxies apart, is not a random number. It is the echo of a specific outcome from that first great superposition. A quantum choice made when the universe was a trillionth of a second old, finally manifesting its consequence billions of years later. The fate of everything was sealed in that initial instant, and we are now witnessing the delayed result of a decision made at the dawn of time. Survival of the fittest may be the law that shaped reality itself. The 15th theory, quantum Darwinism, applies this evolutionary principle not to life, but to the first moments of the cosmos. In the primordial quantum haze, countless potential universes existed in a shimmering superposition. But this state of being everything at once was incredibly fragile. The intensely hot, dense environment of the Big Bang acted as a relentless, chaotic measuring device. It constantly interacted with the nascent wave function of the universe, probing and testing every possible branch of reality. This was not a single, clean measurement, but a continuous, brutal process of environmental selection. Each potential universe, each set of physical laws and initial conditions, was constantly being tested for its durability. One branch might have described a cosmos where particles decayed instantly back into energy. Another might have allowed for forces so weak that no structures could ever form. These fragile realities were quickly suppressed by the environment. They were unstable, and their quantum information was rapidly scattered and lost into the surrounding chaos. But one branch was different. One specific configuration of the wave function possessed a remarkable property: stability. This was the branch that allowed for the existence of persistent particles like protons and electrons. It was the branch where the fundamental forces had just the right strength to allow atoms to form and galaxies to coalesce. This robust universe could withstand the environmental onslaught. More than that, it could proliferate. The information defining this stable reality was copied over and over again as the universe expanded. It was imprinted into the first photons, etched into the distribution of matter, and woven into the very geometry of spacetime. This stable branch produced countless redundant copies of its core data, drowning out the fragile whispers of its unstable competitors. The universe we inhabit is not the one that was necessarily the most likely, but the one that was the most fit. It won a cosmic competition, proving itself robust enough to be measured and recorded by its own environment, ensuring its information would be passed down through billions of years all the way to us. The most likely first thought in the cosmos might have been a terrifying illusion. The Boltzmann brain paradox presents a deeply unsettling possibility. In an eternal or vastly large universe, random quantum fluctuations can, given enough time, assemble almost anything, even a fully formed, conscious brain complete with false memories of a past that never existed. According to this logic, such a disembodied observer, popping into existence for just a moment before dissolving back into chaos, is statistically far more probable than the gradual, ordered evolution of an entire universe filled with billions of real, connected beings. This forces a chilling reinterpretation of the first quantum superposition. That initial state of cosmic indecision may not have been a choice between different types of universes, but a choice between a full universe and a solitary, self-deceived mind. One branch of the wave function led to our vast, coherent cosmos with its 13.8 billion-year history. The other branch led to the spontaneous, fleeting creation of a Boltzmann brain, a consciousness that merely hallucinates a universe like ours. The profound mystery is why we are here, embedded in a consistent reality and not there. The fact that we observe a universe that is old, structured, and shared implies that the first great superposition collapsed decisively away from that bizarre, solipsistic possibility. Our existence is evidence that the cosmos rejected the most statistically likely outcome in favor of a far more complex and stable one. The question of why this happened, why the dice fell so improbably, remains one of the most disturbing and unresolved puzzles at the frontier of physics. Our existence is a loop in time, a cosmic act of self-creation. The 17th theory, the participatory anthropic principle, turns the very act of observation into a foundational force. Proposed by the visionary physicist John Wheeler, This idea presents a universe that was not merely born and then observed, but a universe that required observation to be born at all. In the beginning, the cosmos existed in that now familiar state of pure potential, a vast and shimmering superposition of every possible history. It was a universe of questions without answers. Then something remarkable happened. The first conscious being, perhaps a human astronomer looking up at the stars billions of years later, came into existence. In that moment of observation, in the act of measuring the light from a distant galaxy or pondering the echo of the Big Bang, a wave of reality cascaded backward through time. This was not a physical wave, but a quantum determination. The observer's act of looking into the past retroactively collapsed the initial wave function of the universe, selecting the one specific chain of cause and effect that could have led to their own existence. Think of it like a cosmic choose-your-own-adventure book where the final chapter is written first. By reading the last page, the reader forces all the preceding chapters to fall into a single, consistent narrative that leads inevitably to that conclusion. We are not just passive inhabitants of a finished cosmos. We are active participants, and our gaze backward through time is what solidifies the very history we are trying to uncover. The universe brought us into being so that we could, in turn, bring it into being. The first and greatest quantum decision was not made at the beginning, but at the end by us. Space is not a smooth, continuous fabric, but a tapestry woven from discrete threads. Causal set theory proposes that the foundation of reality is a vast collection of individual points, the atoms of spacetime. These atoms are not scattered randomly. They are connected in a vast cosmic web of cause and effect, a network where each link represents a fundamental relationship, one event influencing another. Before our classical universe existed, this entire causal network was in a state of profound quantum indecision. It was not one set of connections, but a shimmering superposition of every single possible causal set. One potential network might have linked its atoms in a tight, rapid sequence, leading to a universe with a furious, fast-paced flow of time. Another might have been a sparse, sprawling web, resulting in a cosmos where cause and effect unfolded at a glacial pace. For a timeless moment, every possible history, every conceivable chain of events from the most orderly to the most chaotic was equally real. This was the first superposition, a haze of pure potential causality. Then a process of decoherence occurred. This vast, undecided web of cause and effect collapsed, selecting one specific causal set from the infinite menu. This single, definitive network of connections is what we now experience as the unbreakable flow of time and the relentless logic of causality. The reason one event must always follow another, the very foundation of our reality, is the echo of that first quantum decision, which chose not just the things that would happen, but the necessary order in which they must occur. Our reality might be a three-dimensional island floating in a higher dimensional sea. Theory 19, the ekpyrotic universe, envisions our cosmos not as an expanding bubble, but as a vast three-dimensional membrane or brain, adrift in a hidden bulk dimension. Parallel to us floats another brain, a separate universe with its own laws and history. The Big Bang was not a moment of creation from nothing, but a violent, transformative event, the collision of these two cosmic worlds. This leads to a profound reimagining of the first quantum superposition. Before the collision, the two brains were not in a single, defined state. They existed in a quantum superposition of all possible positions and motions relative to each other. One potential reality saw the brains separated by a vast gulf, approaching each other with immense speed. Another possibility had them much closer, gently drifting toward a softer impact. For a timeless duration, every conceivable distance and every possible velocity of approach was equally real. The entire prehistory of our cosmos was a shimmering haze of quantum indecision, a blur of potential collisions. The moment of impact, our Big Bang, was the collapse of this ultimate superposition. From the infinite menu of possible encounters, one specific configuration was selected, one precise separation distance and one exact approach velocity. This single, definitive collision is what ripped the fabric of our brain, flooding it with the immense heat and energy that would later condense into all the galaxies, stars, and planets we see today. The specific initial conditions of our universe, the very seeds of its structure, were imprinted by the exact quantum character of that collision. Our cosmic genesis was not a solitary event, but the echo of a quantum decision made in the space between two worlds. A fundamental symmetry was shattered in the universe's first moments. The 20th theory takes us to the heart of matter itself, to the Higgs field, an energy field that permeates all of space. In the extreme heat of the newborn cosmos, this field was in a state of perfect symmetry. It existed in a profound superposition, a quantum balance where it held every single possible value at once. In this state, the universe was a sea of massless particles, all zipping around at the speed of light, indistinguishable in their energy. There was no distinction between the electromagnetic force and the weak nuclear force. They were unified as a single, elegant electroweak force. But this perfect symmetry was unstable, like a pencil balanced perfectly on its tip. The slightest nudge would send it tumbling. That nudge was cosmic cooling. As the universe expanded, its temperature dropped below a critical threshold. This triggered the electroweak phase transition, the moment the Higgs field's vast superposition collapsed. It had to choose from the infinite menu of possible values. It selected one specific, non-zero value and froze into place. This single decision broke the primordial symmetry. The unified electroweak force splintered into the two distinct forces we know today, electromagnetism and the weak force. More profoundly, as the Higgs field settled into its chosen value, it began to interact with other particles, imparting mass to them. Particles that had been racing at light speed suddenly began to drag, to have substance. This is how electrons, quarks, and all the building blocks of atoms acquired the property of mass. Without this specific quantum decision, this collapse of a universal field, there would be no stars, no planets, and no us. The very substance of our reality was forged in that instant when a field of pure potential chose to become something definite. Our intuitive sense of time may be the universe's most convincing illusion. This 21st theory, the problem of time in quantum gravity, presents a cosmos where nothing ever truly happens. It confronts a fundamental schism at the heart of physics. Einstein's general relativity paints a dynamic picture of spacetime, a flexible stage that bends and evolves. Yet quantum mechanics, when applied to the entire cosmos, suggests a static, frozen reality. The universe's wave function, according to this view, does not change. It simply is. In this timeless picture, the first great superposition and its dramatic collapse were not events. They are merely correlations, fixed relationships between different parts of a single, eternal quantum state. The fiery birth of the Big Bang, the slow dance of galaxy formation, the eventual heat death of everything, all of it is written into this one unchanging block of reality. It is like a novel where the first page, the climax, and the final sentence all exist simultaneously between the covers. The feeling of moving through time, of making decisions and watching events unfold, is just us as conscious beings reading the book page by page. We experience the universe's history not because it is happening now, but because our own consciousness is entangled with a specific sequence of correlations within the frozen wave function. The profound question of why the universe chose one specific path from the initial haze of possibilities is turned on its head. It did not choose. All paths from the first quantum flicker to the last dying star were always there, eternally present in a state of being, not becoming. Our search for a first moment is a quest for a point in a story that was written in its entirety all at once. Every known particle could have a hidden twin. The 22nd theory, supersymmetry breaking, proposes that in the universe's first moment, every electron, every quark, and every photon was quantumly entangled with a perfect, ultra-heavy superpartner. These pairs existed in a state of profound superposition, a single quantum identity shared between a familiar particle and its exotic twin. The cosmos was a perfect, symmetrical dance of matter and a mysterious substance we call supermatter. In this primordial state, an electron was simultaneously its own heavy shadow, the selectron. A quark was also its superpartner, the squark. For a fleeting instant, there was no distinction, no hierarchy, just a unified, supersymmetric haze of existence. This perfect balance could not last. As the universe expanded and cooled, it underwent a cosmic phase transition, a shattering of this perfect symmetry. The vast superposition that linked every particle to its superpartner collapsed. A process of decoherence forced a choice, selecting one specific, broken configuration from the infinite possibilities. In that decisive moment, the superpartners were cast into the shadows. They acquired immense masses, becoming so fantastically heavy that they faded from our observable, low-energy reality. The particles we know and are made of, by contrast, were left with the tiny, precise masses that allow atoms and life to form. The specific mass spectrum we observe today, the reason an electron is so much lighter than a top quark, is not a random accident. It is the frozen echo of that first great symmetry breaking, the specific way the quantum dice fell when the universe chose to hide its own perfect double. Our reality is the leftover, asymmetric half of a much more beautiful and complete whole, a secret twin universe of supermatter forever separated from us by that initial quantum decision. The ultimate cosmic prison might also be a gateway to creation. Some speculative models propose that our entire universe exists on the far side of a black hole, born from the catastrophic collapse of matter in a parent cosmos. In this breathtaking vision, the first great superposition of our reality was not a fluctuation in a void, but the final quantum state of all the information that ever fell through that black hole's event horizon. As a star collapsed in that other universe, the matter and energy crossing the point of no return did not simply vanish. Instead, its quantum information entered a state of profound indecision, a superposition of every possible fate. The firewall paradox, a fierce debate in physics about whether a wall of fire incinerates everything at the horizon, is directly tied to the nature of this moment. One possible outcome saw the information being violently scrambled and destroyed at the boundary. Another saw it passing smoothly through, preserved but hopelessly entangled. For a quantum instant, all these fates were equally real. The collapse of this ultimate superposition did not happen inside the parent universe. It was the birth of our own. The specific resolution of that information's fate, the way the quantum dice fell at the horizon, determined the very initial conditions of our Big Bang. The precise values of our fundamental constants, the seeds of the first galaxies, all of it may be a translated echo of that information's final quantum state. Our cosmos, in all its splendor, could be the other side of a cosmic coin, the answer to a question asked by the dying breath of a star in a universe we can never see. A conscious thought may have been the trigger for reality itself. The 24th theory, the von Neumann-Wigner interpretation, pushes the role of the observer to its ultimate limit, suggesting the universe remained in a state of shimmering potential for far longer than we might think. It did not collapse into a definite state at the moment of the Big Bang or through some random objective process. Instead, it waited. The entire cosmos, with all its superposed laws and fluctuating constants, hung in a balance of pure what if until a very specific threshold was crossed, the emergence of the very first spark of consciousness. This was not necessarily a human mind or even a biological entity. It could have been an immensely complex quantum system in the seething plasma of the early universe, a stable, self-organizing pattern of energy and information that achieved a primitive form of self-awareness. This nascent consciousness, whatever it was, performed the universe's first and most vital act. It observed. In that single, foundational moment of perception, this primeval observer collapsed the universal wave function. Its gaze solidified the previously fluid laws of physics, freezing the strength of gravity, the mass of the electron, and the number of dimensions into the fixed values we measure today. The cosmos did not simply create an observer. The observer, in turn, created the classical cosmos by the very act of looking at it. This idea transforms the narrative of creation from a story of impersonal forces into a deeply intertwined dance between being and being seen, where the universe only became definitively real when it finally had a mind to witness its own existence. The very first tick of the cosmic clock was not a fundamental beat, but a fever breaking from a timeless slumber. The 25th theory, the thermal time hypothesis, reimagines the origin of everything not as a bang but as a temperature drop. It proposes that in its most primordial state, the universe was in a condition of perfect thermal equilibrium. This was not a hot, dense fireball, but a state of maximum entropy, a featureless, timeless soup where every point was identical to every other. Energy was perfectly and uniformly distributed, with no hot spots, no cold spots, and no flow of energy anywhere. In this ultimate state of balance, nothing could happen. There were no events, no before and no after. Time, as we understand it, simply did not exist. The first great superposition was this state of perfect, undecided sameness. It was a universe of pure being with no becoming. Then, a single, random quantum fluctuation disturbed this perfection. A tiny patch of the cosmos became ever so slightly different from its surroundings. It was a fluctuation away from equilibrium, the first and most important imperfection. This tiny difference created the first temperature gradient, the first hint that one place could be different from another. It was this emergence of a non-equilibrium state that spontaneously generated the arrow of time. The flow from order to disorder, from the rare state of near perfection to the common state of chaos, is what we experience as the forward march of time. The collapse of that initial superposition was not a separate event. It was this very process, the breaking of thermal symmetry, that defined the first moment and set the entire history of the universe irrevocably in motion. Our reality is not unfolding within time. Time is the story of our reality's long, slow slide from that one singular moment of imperfection back into the final, cold silence of equilibrium from which it came. Spacetime may be a latecomer to the cosmic party. The 26th theory introduces a strange and beautiful geometric shape known as the amplituhedron. This is not a physical object in our universe, but a purely mathematical structure that exists in a more fundamental realm beyond space and time. In this radical view, the very first superposition was not a fluctuation within a field or a choice between geometries of spacetime. It was a quantum shimmering within the amplituhedron itself. This object encodes, in a single, elegant geometric form, the probabilities for every single way that particles can interact and scatter off one another. All the possible outcomes of every collision that ever happened or ever could happen, from the fiery particle dances of the Big Bang to the gentle decay of an atom in a lab, are contained within its multifaceted volume. In the beginning, this geometric object existed in a state of pure potential, a superposition of all its possible forms and configurations. One facet of this quantum shape might have described a universe where matter annihilated with antimatter in a perfect flash. Another facet encoded a reality where certain particles never interacted at all. For a timeless duration, the entire history of every possible particle interaction was undecided, held in a state of profound quantum indecision within this primordial geometry. The emergence of our classical, four-dimensional spacetime was a direct consequence of this shape settling down. As the amplituhedron's own quantum superposition collapsed, it selected one specific, stable configuration from the infinite menu. This single outcome then projected outward, manifesting as the familiar, continuous stage of spacetime upon which the drama of our universe plays out. The specific rules of how particles move and interact in our reality, the very fabric of cause and effect we take for granted, are merely a shadow cast by this deeper, more perfect geometric truth. Our tangible world of distances and durations is a grand illusion, a user-friendly interface generated by the first and most fundamental quantum decision made by a shape we can only describe with equations. The quantum connections that bind our universe were its first and most fundamental threads. The 27th theory, known as the ER equals EPR conjecture, proposes a breathtakingly elegant link between two of physics' greatest puzzles, quantum entanglement and the fabric of spacetime. EPR, named for Einstein, Podolsky, and Rosen, describes the spooky connection where two particles, no matter how far apart, share a single quantum identity. ER from Einstein and Rosen describes the theoretical bridges known as wormholes, shortcuts through the geometry of spacetime. This theory boldly claims they are one and the same thing. In the beginning, before any classical reality existed, the cosmos was not a place. It was a relationship. The first great superposition was an immense, all-encompassing web of quantum entanglement, linking every single one of the universe's fundamental building blocks. Each potential particle was spookily connected to every other in a dizzying network of pure correlation. One branch of this universal wave function might have described a cosmos where entanglement was sparse and local. Another branch saw every element entangled with its most distant possible neighbor. For a timeless moment, the entire cosmos was a shimmering, non-local graph of pure connection, a cosmic brain where every thought was linked to every other thought simultaneously. There was no distance, no here or there, only this vast, undecided web of potential relationships. Then, the process of decoherence began. As this immense superposition collapsed, it did not just select one set of physical laws. It performed a cosmic act of geometry. The quantum entanglement between particles was literally sewn together, transforming those spooky, non-local links into the smooth, continuous fabric of spacetime itself. The wormholes, the ER bridges, became the very glue that binds space into a coherent whole. The reason we perceive a universe with three spatial dimensions and a relentless forward flow of time is that this was the most stable, classical structure that could emerge from that initial, chaotic web of quantum handshakes. Our reality is not built of stuff in a container. The container itself is a fossil, the geometric remnant of the universe's first and most profound conversation. The code that runs our reality might have been written by an unfathomable intelligence. This 28th theory, the simulation hypothesis, takes the quantum mystery of our beginning and frames it in the language of information. If our universe is an advanced simulation, then the first great superposition was not a physical event, but a computational one. Before the first frame of our cosmic history was rendered, the simulation's memory held a single, immense quantum state vector. This was not a field of energy, but a data structure of pure potential, a digital blueprint containing every single possible set of initial conditions. One line of this cosmic code might have defined a universe with 5 fundamental forces. Another line could have set the mass of the electron to a value that would prevent atoms from ever forming. For a processing cycle that existed outside of our time, all of these potential realities were loaded and active, a shimmering haze of undecided variables waiting in the memory buffer of a quantum computer of cosmic scale. The Big Bang, in this view, was not an explosion. It was the execution of a specific algorithm, a subroutine designed to collapse this vast superposition. This code sampled the probability distribution of the initial state vector, performing a random number generation on a universal scale. With that single computational operation, it selected one specific set of parameters from the infinite menu. It locked in the speed of light, the strength of gravity, and the value of the cosmological constant, defining the rules of the simulation we now inhabit. The strange fine-tuning of our universe, the constants that seem so perfectly set for life, are not evidence of a divine creator, but simply the specific random seed chosen by the simulation's initialization protocol. Our reality is the output of a program that made its first and most important calculation at the dawn of everything, rendering a single, consistent universe from a sea of digital potential. A perfect mirror of our reality may have been the universe's first and most profound reflection. This 29th theory, built upon the principle of CPT symmetry, proposes that the Big Bang did not create one universe but a pair. CPT stands for charge, parity, and time, and the law states that if you reverse the charge of every particle, flip its spatial coordinates as if in a mirror, and reverse the flow of time, physics should remain exactly the same. The theory suggests this is not just a mathematical quirk, but a literal description of creation. The very first quantum superposition was not a choice of laws, but a choice of direction. One branch of the wave function described a universe like ours, made mostly of matter and evolving forward in time from the Big Bang. The other branch described its perfect twin, an anti-universe made mostly of antimatter and evolving from our perspective backward in time. For a fleeting quantum moment, these two symmetric realities existed simultaneously, a cosmic Rorschach test of pure potential. Our universe and its mirror image were a single, undecided whole. Then a tiny imperfection, a cosmic crack in the perfect mirror, emerged. This asymmetry is thought to reside in the behavior of neutrinos, those ghostly particles that barely interact with matter. Certain neutrino interactions may violate the perfect symmetry of charge and parity, meaning they behave slightly differently from their antimatter counterparts. This subtle flaw was the trigger. It caused the vast superposition between the universe and the anti-universe to collapse, decisively selecting our matter-dominated timeline. The profound consequence of that first quantum decision is written across the cosmos today. We live in a universe filled with stars and galaxies made of matter, with almost no antimatter to be found. This great cosmic imbalance, one of the deepest mysteries in physics, is not an accident. It is the direct result, the frozen echo of that initial symmetry breaking. The reason we exist at all is because the universe, in its first moment, chose to look into the mirror and see a reflection that was not quite perfect. So we arrive at the 30th and final theory, a synthesis that weaves together the most compelling threads from our journey. The truth of that first cosmic moment may not be captured by a single idea, but by the resonance between them. Perhaps the universe's first superposition was a multifaceted event, a symphony of quantum decisions playing out all at once. It began as a quantum gravity state, a churning foam of all possible spacetime geometries, as the Planck epoch theory suggested. Within that foam, the entire landscape of string theories, 10 to the 500 possible vacuum states, shimmered with potential. The selection of our specific vacuum, with its exact number of dimensions and precise force strengths, was the first great collapse. But what drove that decoherence? It was likely the simultaneous emergence of time itself, breaking the frozen symmetry of the timeless wave function and creating the first irreversible arrow, just as the problem of time implies. This transition then triggered the breaking of supersymmetry, casting the heavy superpartners into shadow and giving our familiar particles their mass. And through it all, the participatory principle suggests that this entire cascade was a self-sealing loop, a reality that only became definitively real once the conditions for future observers were irrevocably locked into place. This unified view does not declare a single winner. Instead, it paints a picture of a cosmic genesis far richer and more interconnected than any one theory could portray alone. The birth of everything was not a single note, but a chord struck from the deepest laws of physics, a harmonious convergence that selected one stable, observable, and participatory universe from an infinite sea of silent potential. From the inflationary vacuum to the holographic boundary, we have journeyed through 30 mind-expanding theories about the universe's first quantum superposition. What stands out with stunning clarity is that this primordial event is not just one mystery among many. It is the foundational mystery, the singular question mark from which all of existence emerged. This single concept ties together the vast scales of cosmology with the bizarre rules of quantum mechanics, forcing us to confront the very nature of reality itself. The search for a definitive answer is far from over. It continues to drive experiments with particle colliders, detailed analyses of the cosmic microwave background, and the development of ever more refined theories of quantum gravity. Each new discovery, each subtle anomaly in the data, brings us one step closer to understanding that first fleeting moment of pure potential. As you reflect on this cosmic journey, which of these theories resonates most deeply with you? Does the idea of a timeless multiverse speak to your imagination, or does the profound simplicity of a cosmic hologram feel more compelling? Share your thoughts in the comments below, and if your curiosity about the cosmos's greatest puzzles has been ignited, be sure to subscribe for more deep dives into the fabric of reality.